Okay, so we're starting chapter 6 today, and we're starting with 6.1, the introduction to the normal distribution. So the normal distribution is our favorite distribution. It's got a lot of straightforward and relatively easy to understand properties. And so that's what we're going to be looking at in this section is what is the normal distribution, what are its properties, what can we do with it, and to do that we have three objectives to look at. First, of course, is the properties of the normal distribution. We want to be able to determine if something is normal or normally distributed. And finally, we're going to talk about something called the standard normal. And how to standardize a distribution. Specifically, normal distribution. So, the normal distribution is a continuous probability distribution. So let's pause there for a second. Notice this is different from chapter 5 where we looked at discrete probability distributions. This is a continuous distribution. I probably did not a great job explaining the difference between discrete and continuous in that last chapter, but essentially, as I described it, continuous is a forever thing. It continually moves on, whereas a discrete is finite or infinite, but if it's infinite, it's countable, whereas continuous, in this case, not countable. So it's for a continuous random variable x. We still use capital X as our convention. A continuous random variable's outcomes cannot be listed because they are, well, typo there, that should be fixed in yours. They are infinite, and they are not countable specifically, unlike the discrete distributions. And a normal distribution is entirely defined by its mean, mu, and its standard deviation, sigma. So what we want to talk about now is the properties of the normal distribution. So first and foremost, the normal distributions are symmetric. They are bell-shaped. They're bell curves. They have their line of symmetry at x equals mu. So right at the mean. Most of your data is going to be in the middle, as we know from the empirical rule. The empirical rule tells us with a bell shape how much data is within 1, 2, and 3 standard deviations going out from the center. And symmetric and bell-shaped, if you are both of these things, it means that the mode occurs at the center. Well, if the mode occurs at the center and the symmetry, the line of symmetry, which is the center, is the mean mu, one very interesting property is that the mean equals the mode equals the median. So being symmetric and bell-shaped means that the maximum number or the most repeated value has to occur at the center. Otherwise, the most repeated would be somewhere else and it wouldn't be symmetric. Since its symmetry line is at the mean, that means the mean and the mode have to coincide. And the median, which is the geometric center, to be symmetric in graph shape, also needs to be at the center. So we don't have any other measure of center for normal distributions other than the mean, mu, which is one of the reasons we like normal distributions so much. Additionally, as we said above, they're completely defined by the mean and the standard deviation. And so the starting then, that's supposed to be a then. I was trying to figure out. Then starting from the mean and moving out in either direction exactly 1 standard deviation in distance gives the what are called inflection points. Now, if you're taking some calculus courses, you know what inflection points are. For those of you who don't, these signify a change from either curving up to curving down. So as a little diagram here, we can draw a fake normal distribution. So this would be the mean mu. We'd go 1 standard deviation down, so this would be mu minus sigma. 1 standard deviation up would be mu plus sigma. Sigma, I started to do mu again. Sigma. And let's say this is our curve. Pretend that I'm drawing this perfectly symmetrical, even though I didn't. That means that these points here, which they're supposed to be even, but these are the inflection points that we're talking about. So inflection points tell us here we're increasing. We're getting more and more data points as we come from further from the left. And then we start decreasing. We're slowing down how many data points until we hit this maximum value here. And then now we are decreasing, but we're decreasing quickly. And this then starts curving back up. So we're curving down here and then curving back up. So I have it written here as from curving up to curving down, but it also is from down to up. And so inflection points are used to determine how the shape of graphs look. For normal distribution, they are widely known. It's been well studied. They always occur 1 standard deviation up and down, which again is a nice easy place to have them. It's one of the reasons we like normal distributions. So up next is the total area under the curve. The curve that you have here is called the density curve. And the total area always has to equal 1. Because again, these are probability distributions. So all the probabilities added up have to be equal to 1. So the whole under the curve must be equal to 1. Just reiterate. And the probability that our random variable, our continuous random variable x, is less than or equal to some value x on the number line that we pick, this is equal to the area to the left of x. Now we're going to be looking at areas a lot more in the coming sections, starting with 6.2. So if this statement here is a little wonky to you and doesn't quite make sense, just wait till the next section and it'll be made clear. The x-axis is a horizontal asymptote, is our last property. So you should remember horizontal asymptotes from your algebra days and your other math classes if you had them. But all this means is that it will never cross the x-axis. And the reason no distribution ever crosses the x-axis is because the value at the x-axis we know is 0. But no outcome in a probability distribution ever have a probability of 0. Remember, the only thing that has probability of 0 is the empty set, which has no outcomes in it whatsoever. So if something's happening, it has a non-zero chance to happen. It could be very small, could be very, very close to that axis, but it's never equal to 0. So these are the big properties. Like I said, they're nice. Mean, median, and mode all coincide in the same point. They're totally defined by standard deviation and mean, so we don't have to worry about other statistics to calculate. They're relatively straightforward. So let's talk about how do we determine if something is normal. So first and foremost, the first thing you check is it must be continuous, not discrete. So if you see a discrete random variable, not a normal distribution. Can't be. After that, most of your data values must lie close to the mean. And for practical reasons, what this really translates to is few outliers. Because if most of your data is close to the mean, then there are not going to be very many outliers to the left and right on the outsides. And then the final thing, if you've gotten through these two things, is it must be bell-shaped and symmetric. So you can have discrete, or you can have continuous distributions that most of their data does lie close to the mean, that are not bell-shaped, or they are not symmetric. If either of these fails, then it's not a normal distribution. It's not a this or this, it's a this and this. They both have to happen. So that does mean that we have a lot of different types of normal distributions that can appear. So we're just going to sketch out a couple so you can get an idea. Not every normal looks like what we just drew. So this is what we drew on the other page, something like this. But we could also have something like this. We could have something like, I've got another color here. Something like this. We could have something like this. Or something like this. Or something like this. Let's do it in a third color. We're assuming that this line here, that's totally, completely, 100% straight, and this line here are axes. And so this would be mu1, this would be mu2, not the Pokemon, this would be mu3. Over here, all the mu's are in the same, but all these distributions are very different. They're all bell-shaped, they're all symmetric about their means, but they're all very different. And so when we have all these different possible all these different possible distributions, we need a way to, what we call, standardize them, to be able to talk about them all at once. And that's where the standard normal, and this is a capital T, the standard normal distribution. So what is it? Well, first, just like all normal distributions, it's bell-shaped and symmetric, has to be. But its mean is strictly mu equals 0, and its standard deviation is sigma equals 1. So this is the standard normal, with a mean of 0 and a standard deviation of 1. The total area under the standard normal curve, of course, equals 1, because it's a normal distribution. And the x-axis is, of course, a horizontal asymptote. So really, the standard normal distribution is the normal distribution whose mean is at 0 and whose standard deviation is equal to 1. Otherwise, it's just any old normal distribution. And so we need a way of converting, or what we call standardizing, non-standard normals to the standard normal. So in essence, we are remeasuring or relabeling all of these different distributions to match in terms of what the standard normal does. And so to do that, we've actually already seen what we do. We standardize any normal distribution to the standard normal, that should be capital, by calculating the standard score, or the z-score. Right? We saw that back in chapter 2. And the z-score, of course, formula is z equals x minus mu over sigma. And I said back then that this treats our z-score, our standard score, as like a distance in terms of standard deviations. And that's exactly what this does, because it takes this standard deviation and treats it as the bottom line. Now, if the standard deviation is 1, like the standard normal, then our z-score is just x minus mu. It just sits perfectly on our x-axis. But if we don't have the standard normal, then by dividing by our standard deviation, essentially creates this as 1. it forces the standard deviation to go to 1. And now we're not talking about either the mean that we have, the standard deviation we have, or the value in question. We use the z-score, the standard score, to represent that as a kind of pseudo measure of what this would look like if it were the standard deviation or the standard normal distribution. So graphically what's happening here is, let's say we have some mu and this is non-zero. Here's mu plus sigma, here's mu minus sigma, and our normal distribution looks something like this. Well, when we standardize all of these values, whatever they are, it forces it strictly to 1 or 0, 1, and negative 1, and is the standard normal. So by standardizing all of our x values, all of our data values, we take a non-v, capital V, standard deviation, standard distribution, and force it into the standard normal. That's what the z-score does. And so we're going to be talking a lot about z-scores. They're not going to go away for the rest of the course. So we'll be talking at those at length. For now, we're just going to go back and convert some standard scores, some z-scores, and now we're going to interpret what this actually means. So we're going to convert 4 scores using a mean of 25 and a standard deviation of 3.2, and then we're going to interpret what each of those values means. So we're going to start with 27. So our z-score then, 27 minus 25 over 3.2. So it's 2 over 3.2, and this is approximately 0.63. Now, one thing you always want to do with your z-scores is round to 2 decimals. And so 0.63 means that we're to the right of the mean, and we are less than 1 standard deviation away. Now, you may be thinking, well, duh, I can see the standard deviation, I can see the mean, and I can see the score. We're bigger than it, we're to the right, and of course we're less than 1 because we're less than 3.2. But what the standard score is about, remember this came from relative position, so this tells you without having to know any of this, if I tell you the z-score of a particular probability, because these are probability distributions, is 0.63, you know all of this information. You don't need to know any of the values. And that's the point of the standard score, is it tells you the position, the relative position it is, in terms of standard deviations. Oh, 0.63, we're to the right of the mean, and we're less than 1 standard deviation away because we haven't hit 1 yet on the standard score. That's the point of the z-score. So the second one here, 45 minus 25 over 3.2. This is 20 over 3.2. And so rounding to 2 decimals in my calculator, this is 6.25. So this is very far right. Of the mean. And it's greater than 6 standard deviations. That's just an errant mark. That's a greater than symbol. Greater than 6 standard deviations away. All right, this is really far. In most cases, we would consider this an outlier. Super far to the right. But now if we go to number 3 and we go to 63, minus 25 over 3.2, this is 38 over 3.2, or approximately 11.88. Well, this is incredibly far to the right. Of the mean. Greater than 11 standard deviations away. And so this is 100% certainly to be an outlier. All right, 6.25, we would probably make a fair assessment that it is an outlier, but at 11.88, we're almost 12 standard deviations away. This thing is way out to the right, and it is having absolutely nothing to do with the other data points, a complete outlier. And then our final value here is 22. So calculating our standard score, this is -3 over 3.2, which is approximately -0.94. So now we have our first instance of negative. Negative means to the left of the mean. And again, less than 1 standard deviation away. So just to reiterate here, when you know the value, the mean, the standard deviation, the z-score is a sometimes useful thing to calculate, but really what the z-score is about is telling you information without having to actually know any of the data. I don't need to know what my score is to look at a standard score, a z-score of 11.88 and say, holy crap, that's really far away. It's definitely an outlier from the data. I don't need to know what the other data is. I don't need to know what the data is representing. I know that this big of a z-score, super far away, probably not going to have anything to do with the other data points. Complete outlier. Similarly, I can look at -0.94 and go, okay, we're a little bit less than the mean. We're still within 1, so there's probably going to be a lot more data points that are similar to this because we're 1 standard deviation within 1 standard deviation from the mean. Okay, so we'll be looking at areas in the next section, and we'll be coming back to z-scores and standard scores. Like I said, these things are not going to go away. We're going to see them for the rest of the class.